Our upcoming schedule a little bit. So on Thursday of this week, you are going to have Quest 2. Okay, so we have scheduled review and Quest 2, but I want to remind you that our class was chosen as part of a sample to take a survey that GCC thinks is going to give them some important information about the student experience here. So that survey can take anywhere from like 15 to 30 minutes. And we have like 30 minutes to spare before we have to start the quest. So we will be working on that survey. We will be doing that survey. And then as you finish the survey, you'll move on to independent review. You'll have a little bit of time to study before you start the quest. And I will like come around and answer questions individually. Max, yeah, max. Yeah. And remember that it is optional. They can't make you do it. So if you need those 30 minutes to study, just say, I'm not doing it. Okay. It's totally up to you. You're allowed to do that. So there will be survey / study time and then the quest. Today's class, we're going to cover 2 new topics that will not be on the quest on Thursday. So don't stress about that you might get tested on this next class. Okay, so what we're going to talk about today is not on the quest. The quest is going to cover lessons 6 through 9. Okay, so 6 was equations of lines. 7 was additional properties of lines, and that's where we talked about horizontal lines, vertical lines, parallel and perpendicular lines. Then we talked about lines of best fit when you have some data, and then in context linear problems, which was again finding equations of lines. You just had to pull out from the little paragraph 2 points, right, and find the equation of the line. So it's all about equations of lines. That's the big umbrella topic. All right, so any questions about the quest or the schedule? Oh, I wanted to tell you resources for preparing for the quest, right? So I logged into our Moodle site, and if you scroll down to the bottom, there's quest / test prep material. There's the practice problems packet. Everyone has a printed copy, assuming you didn't lose it, but it's here if you need a fresh one. Practice problems blank. So when you open that up, our quest is going to be on lessons 6 through 9. So you look up lessons 6 through 9 here, and you can do the problems next to lessons 6, 7, 8, and 9, right? And those are practice problems for the topics that will be on this quest. If, as you're working through those problems, you have any trouble, you get stuck, you don't know how to solve it, right? You can either click on the practice problem solutions packet, and here all the solutions are written out, right, to each problem in the packet. They're all solved with the work shown. And if that's not enough, you can click on the practice problem solutions videos, and it takes you to a playlist in YouTube where there's a video of each problem in that packet being solved. Okay, so those are your resources to help you prepare. And for all quests and tests, you're allowed to bring 1 page of notes with you, front and back. You can put whatever you want on it. The only stipulation is it has to be written or typed by your hands. Okay, you can't take cell phone pictures of your notes and like paste them all on a piece of paper. You have to write or type it with your hands. Can't use a photocopy of somebody else's notes that they made. All right, so that's it for what's coming up. The quest, how to prepare, what's going to be on it. Okay, so jumping to today's material, again, this will not be on the quest, though we will get some practice, a little more practice graphing lines today, because that's part of the technique that we're going to learn. Okay, so in this line, we're going to use graphing to find the solution system of linear equations and learn to interpret the solution's meaning. All right, so this was designed to have no demo this lesson, but I think I'm just going to do the first page with you and then let you take over and work through the rest of it on your own. All right, so the daily rates for renting a compact car from 2 different rental companies are shown in this table. Okay, so company A charges you 30 cents per mile, and there's a 0 fixed per day charge. It's just strictly 30 cents per mile. Rental company B charges you $20 no matter what, plus 10 cents a mile. Okay. The question is, which company would you choose to rent from? So we're going to figure out the answer as we work through the steps in this problem. We're going to write a linear equation for each rental company that expresses the total daily cost, Y, of renting a car and driving in a distance of X miles. Okay, so Y is going to be cost, X is going to be miles driven. So rental company A, I wrote that as Y sub A, just as you can tell the difference between the two Y's. Right? So the cost for company A, how would I write that as an algebraic expression? 0.30x, great. 30 cents per mile times X miles. Because you don't know how far you're going to drive, we're going to call that X. All right, and then rental company B, how would I write the cost to rent a car from company B? Yes, $20 plus 10 cents for every mile, so 20 plus 0.10x. All right, so these are lines, right? Each of these is a line. It looks like y equals mx plus b. In fact, Riley said that in the mx plus b form, and I think I'll put it like that. 0.10x plus 20. So now it's mx plus b form. Your slope is 0.1, your y-intercept is 20 for company B. For company A, your slope is 0.3. What's your y-intercept for company A? 0, yeah, because there's like an imaginary plus 0 there. Good. All right, so I'm going to fill in a table of values for each equation. So for company A, if I were to drive 0 miles, how much would it cost me to rent a car? $0, right? Okay, so I have a point, distance, comma, cost, in this case would be 0, 0. 0 miles, $0. Now, what if I drove 140 miles with company A? How much would that cost me? 140 times 0.30, can I do it in my head? 42. So $42. So my point is going to be 140, comma 42. All right, I'm going to figure out the same distances. Using the same distances, I want to figure out the cost for company B. For company B, if you drive 0 miles, how much does it cost? $20, right? Because they charge you $20 no matter what, even if you're just going to sit in the parking lot. It's $20. Okay, so the point ordered pair is going to be 0, comma 20. All right, how about $140? How much would it cost? I'm sorry, 140 miles. How much would it cost for 140 miles? $34. Yep. 0.1 times 140 is 14, plus your $20 flat fee, so $34. Okay, so my point is going to be 140, comma 34. All right, so these are two separate companies, two separate cost lines. So I'm going to draw two separate lines on this grid paper below here. Okay, so I'm going to have X, which is distance driven, and Y, which is cost. All right, so company A, I'll do them in two different colors. Company A, we've got 0, 0, my first point, and 140, comma 42 as my second point. And I'm going to connect them with a straight line. You should use a straight edge. I'm going to try to make my smartboard do a fancy line here. All right, there we go. All right, so that is going to be company A. Okay, company B, we have 0, 20 and 140, 34. 30, 35, so there's 34. All right, so there are my two lines. This one here is company B. Okay, so looking at the graph, what's the solution to this system, right? So I have the system y equals 0.3x and y equals 0.10x plus 20. So I've got two different equations, and two unknowns. There's two equations there. My two unknowns are x and y. I want to find the solution to the system. What x and y lies on both lines? What xy point is on both of those lines? Yeah. This point right here, where they cross, that point is on both line A and line B. And it's got coordinates 100, 30. Okay, so my solution is the point 100, 30. What does that mean? What does that point signify in terms of the distance and in miles and the cost? What does that mean? At 100 miles, it costs the same from both companies. Both companies will charge you $30 to go 100 miles. Very good. Okay, so I'm just going to quickly verify that the point 100, 30 is a solution algebraically. So I saw it's a solution graphically because that is a point that both lines share. Algebraically, what it means to be a solution to a system is that if you plug in the x coordinate for x and the y coordinate for y, both equations are true. So let's start with y equals 0.30x, y equals 0.10x plus 20. And I have an x and a y that I claim is a solution. That means that it has to make both equations true. So if I take my 100 and my 30 and I plug in the y coordinate for y and the x coordinate for x, is that equation true? Yes, 30 does equal 0.3 times 100. So this is 30 equals 30, check. So my point, my solution, makes my first equation true. I have to show that it also makes my second equation true for it to be a real solution. So I put in my 30 for the y, put in my 100 for my x. Okay. 0.10 times 100 plus 20, does that in fact equal 30? Yes, that is true. 30 equals 30, check. So that's how you show that a given ordered pair is a solution to a system of equations algebraically. So we found that ordered pair by graphing two lines, seeing where they crossed, finding the point that those two lines share, their intersection point, and then we verified that that point was a solution by plugging in. All right, so I think that that's good for the demo. I'm going to have you pick up at number 4 and work through some of the activities on your own. This is what we call an in-context linear problem. Okay, I gave you a little hint by circling things in different colors to just remind, like, oh, I have 2 points, right? I can pull 2 points out of this paragraph. So I have two different variables, right? I've got time in hours. Right, and my other variable is tail wags, right? Number of tail wags. Okay, which one do you want to make x and which one do you want to make y? we typically always make time the independent variable, the x. If it's not explicitly stated differently in the question, you can assume time is the x, or the independent variable. So my points are 5, 27, 5 hours, 27 tail wags, and 7 hours, 37 tail wags. So I have 2 points, and I want to find the equation of the line that goes through these 2 points. What's the first thing I always have to try to find when I'm looking for the equation of a line? Slope, right? Because the equation of a line is y equals mx plus b. So I start by trying to find the slope. Okay, so my slope is the change in y over the change in x. I don't know why y goes on top, but it always does, right? Y goes on top. 37 minus 27 over 7 minus 5. So I get 10 over 2, which is 5. So my slope is 5. I come back to my equation. I replace my m with a 5. Now I just have to figure out what b is, right? So to figure out what b is, I can use either of my 2 points. And I can plug in the x coordinate for x, the y coordinate for y, and solve for b. So I'll use, say, 5, 27. 5, 27. You can use either point. It does not matter. It'll get the same answer for b. So I put in my 5, the x coordinate for x. And the y coordinate is 27. I replace the y with that. And I try to solve for the b. So this says 27 equals 25 plus b. So b has to be 2. Should I circle that and be done? Put it in the equation, right? That's not the answer. It's a piece of the equation that I was looking for. I got to go back up to my equation. Y equals 5x plus. Now I know what b is. It's 2. Y equals 5x plus 2. And you can always check your answer when you're done by plugging in a point, right? If I plug in 5 for x, do I get 27 for y? Yeah, 5 times 5 plus 2 is 27. Plug in 7 for x. 5 times 7 is 35, plus 2 is 37. So both of my points are on that line. So that, yeah, that's the answer. I was looking for the equation of the line. It should look like y equals something times x plus something else. Good. So I'm going to go through the demo. If there's time when I'm finished, you can either go back to what you were working on if you hadn't finished, or you can start the activities for lesson 11. Okay, so in this lesson, we're going to solve systems of equations algebraically. So last class, what you were just working on was solving systems of equations, but you did a graphical method. So I'm going to teach you another method, because the drawback of the graphical method is that sometimes your answer was a little bit off, right? Because sometimes you had to estimate where your points went. If you didn't draw a perfect line with a straight edge, sometimes your solution was a little bit off. So we're going to come up with a more accurate algebraic method here. All right, the first one is called substitution. Okay. We have this system, 6x minus 2y equals -3, and 4x plus y equals 5. I could treat those both like lines, graph them, and see where they cross. Instead, I'm going to use this new algebraic method. Okay. First, solve either equation for either variable. Okay. That means we have 4 choices. I could solve the first equation for x or for y, or I could solve the second equation for x or for y. It is entirely your choice, but some of the choices are easier than others, right? So in this case, like if I said, look at the first equation and solve for x, the last step of that would be to divide by 6, right? If I was trying to solve this equation for x, at some point I would have to divide everything by 6, and that would introduce some fractions. And I would rather not introduce fractions. So instead, I'm going to look at the second equation and solve it for y, right? Because I'm not going to introduce any fractions because the coefficient on the y is a 1. Okay, so I'm going to start by writing down the second equation, 4x plus y equals 5. And I just want to get the y by itself. So I would subtract 4x from both sides. So y equals 5 minus 4x. So that's the first step. Pick one of the equations and solve for one of the variables. You can make any choice you want, but sometimes it's nice to be able to look ahead a little bit and figure out which choice is going to be easiest for you. All right, the next step is to substitute into the other equation. So not the equation I just picked, but the other one. So I have 6x minus 2y equals -3. And I'm going to substitute. That means I subtracted 4x from both sides. So those went away, and I got y is 5 minus 4x. All right, so now I picked the other equation. I'm going to substitute. Wherever I see a y in this equation, right here, wherever I see a y, I'm going to replace that y with a 5 minus 4x, because y and 5 minus 4x are the same. They're equal, so I can substitute one for the other. So this is going to become 6x minus 2 times 5 minus 4x, right? Instead of a y, I put a 5 minus 4x, and that equals -3. So I made a substitution. Instead of a y, 5 minus 4x, because they are equal. Now in my new equation, after I make the substitution, it only has x's in it. There are no y's in it anymore. So I can solve it, because it only has one variable. I can solve it. So the first thing I would do is maybe distribute that -2. So I have 6x minus 10 plus 8x equals -3. So I just distributed that -2. Combine like terms on the left side. 6x plus 8x is 14x. Then what? Add 10 to both sides. Plus 10 plus 10. So I get 14x equals 7. And then divide by 14. So those cancel, and you get x equals 7 over 14, or 1 over 2, or 0.5. Yeah. So I now know what one of my two variables was, right? I started with two equations up here and two unknowns. We got two equations and two unknowns. I now know what one of my unknowns is. I know what x is. I still would like to know what y is. So now that I know what x is, I can substitute to find the value of y. So I substitute x equals 1/2 into any equation that has both x's and y's in it. Any equation that has both x's and y's in it. You can make your own choice. The easiest equation would be this one right here, where y equals 5 minus 4x. And then I can replace the x with a 1/2. Because I now know that x is 1/2. So this is 5 minus 2, which is 3. So x is 1/2 and y equals 3 is the solution. Or you can think of that as the point, 1/2 comma 3. That would be the intersection point if you graphed both the lines. They would cross at 1/2 comma 3. All right, then we should check that our answers are actually solutions by plugging into the original equations. So I rewrote the original equations here. I'm going to replace the x with a 1/2 and the y with a 3 and make sure the equation is true. So 6 times 1/2 minus 2 times 3. Does that actually equal -3? What do you think? Yeah. 6 times 1/2 is 3, right? So this is 3 minus 6 Does that equal -3? Yes. All right, and then I have to check the other equation too. Plug into the other equation, replace the x with a 1/2 and the y with a 3. Does that actually equal 5? Does 4 times 1/2 plus 3 equal 5? Yeah, because 4 times 1/2 is 2, and 2 plus 3 is 5. So that's called the substitution method. To summarize, right, you start with 2 equations and 2 unknowns. 2 equations and 2 unknowns. Pick one of the equations and solve for one of the variables. And then you substitute that expression into the other equation and solve. So you will definitely have more of these to practice with in a few minutes. However, I know you're super excited because there's another method, right? So we have one more method, one more algebraic method. It's called the elimination method. It's also called the addition-subtraction method. Okay? It's a second way to solve linear systems algebraically, and it's based on the property that equals added to equals are equal. Okay, so I have a new system here, 9x plus 6y equals 54, 6x minus 5y equals 9. For elimination to work, the numbers touching one of the variables have to be opposites. Okay. So I'm going to multiply each of those equations by some number to make the numbers touching one of the variables be opposites. In this example, if you multiply the first equation by 2, the whole first equation by 2, and the whole second equation by -3, this will do the trick. And it's okay if you don't know where I came up with 2 and -3 right now. We're going to talk about it in a few minutes, where those numbers came from. Okay, let's just see what happens when I do this. So I've got 9x plus 6y equals 54. I'm going to multiply every single term in that equation by 2. So I get 18x plus 12y equals 108. Multiplied everything by 2. And in the second equation, multiply everything by -3. -3 times 6x would be -18x. -3 times -5y is 15y. -3 times 9 is -27. Okay. So the reason I did this multiplication is because it made the numbers touching my x, one was +18 and one was -18. Right, so my goal was I wanted the numbers touching my x to be opposites. Same size, but one positive, one negative. So we've got a +18x and a -18x. So my goal was to make my 9x and my 6x turn into the same thing, but with opposite signs. So can you kind of see where the 2 and the -3 came from now? I looked at 9x and 6x and I said I want them to be the same number, but with opposite signs. So I came up with the least common multiple of 9 and 6, which would be 18. Multiply the 9 times a 2 and a 6 times a 3, you get both of them are 18. So now my next step is to add the 2 equations together, right? So I do plus, just add the 2 equations together. So 18x plus -18x is how many x's? 0. Those cancel. That's why I wanted them to be opposites. 12y plus 15y is 27y. And 108 plus -27 is 81. Yeah. All right. And then where'd 27 come from? Oh, divide by 27. Yeah. Divide by 27. Divide by 27. So those cancel, and I get y equals 81 over 27, 3. So I now know one of my solutions, one piece of my solution. My solution should be an x and a y because I have 2 unknowns. So you substitute to find the value of the other variable. Pick any equation that has both x's and y's in it. and replace the y with a 3. So I'm going to have 6x minus 5 times 3 equals 9. 5 times 3 is 15, so 6x minus 15 equals 9. Then what? Add 15 to both sides, so I get 6x equals 24. Divide by 6, so I get x equals 4. So there's my other unknown. So I now know my solution is x equals 4 and y equals 3, or the point 4 comma 3, right? If I had solved this graphically, I would have started by graphing these two lines and seeing where they crossed, and that would have happened at the point 4 comma 3. You should go back and check that you actually have a solution, 4 comma 3. So my equations were 9x plus 6y equals 54. And 6x minus 5y equals 9. And then I check. Replace my x's with 4s and my y's with 3s. Make sure both equations are true. Okay, so this becomes 9 times 4 plus 6 times 3. Does that equal 54? That's 36 plus 18. That is 54, yeah. Check. Okay, so it works for the first equation. Has to also work for the second equation. So 6 times 4 minus 5 times 3. Does that equal 9? Okay, so 6 times 4 is 24. 24 minus 15, is that 9? Yes. So we do actually have a solution. Okay. Usually, two lines intersect at a single point, but there are two special cases that you looked at in the previous activities. When you have two parallel lines, in which case there's no solution, and two lines that are really the same line, in which case there are infinitely many solutions. This is a long lesson. So we're almost done. Okay. So if I was going to use substitution to solve each of these systems, so I've got two systems below, something strange is going to happen when we solve it. Then we're going to make some conclusions. Okay. So if I use substitution, the first method I showed you, you pick one of your equations and solve for one of your variables. Okay. So this first equation is already solved for y, right? So in my second equation, I can replace the y with a 2x plus 1. They are both, so I could have done it either way. Yeah. So I'm going to make my substitution. Instead of y, I'm going to replace the y with a 2x plus 1. Why? So if y equals 2x plus 1, then when I see a y, I can replace it with a 2x plus 1 because they're the same value. Okay. So now I have an equation with only x's in it. That's why I make the substitution, because once I substitute, I have only x's, and I can try to solve it for x. So what happens when I try to solve this? Yeah, how do you know that's false? Just by looking at it. Yeah, right, exactly. How can 2x plus 1 be the same value as 2x plus 3? Is it possible? No. And what happens when I try to solve it, if you didn't recognize it right off the bat, which is great, and you can just write impossible here, if you didn't recognize it right off the bat and you tried to solve, you might try to subtract 2x from both sides, and you would get 1 equals, because those go away and those go away, and you'd get 1 equals 3, right? That's not true, right? That's not true. Okay. So what kind of special situation do you think this is? No solutions or infinite solutions? No solutions. If you get an equation that can't ever be true, this has no solutions. There is no point, x comma y, where these two lines share a point, right? These two lines are actually parallel lines. They have no solutions. All right, similar approach in B here. I'm going to look at my y equals 2x plus 1. So y and 2x plus 1 have the same value. They're equal. So in my next equation, I can replace the y with a 2x plus 1 because they're the same. So this becomes 6x minus 3 times 2x plus 1 equals negative 3. Now I just have x's here. I can try to solve this for x. So I'm going to start by distributing my negative 3. So I have 6x minus 3 equals negative 3. And what's 6x minus 6x? 0. Those go away. So this becomes negative 3 equals negative 3. It's true, right? I mean, it doesn't tell me anything, but it's true. So what special situation do you think this is? No solutions or infinite solutions? Infinite solutions, because negative 3 always equals negative 3. Doesn't matter what x and y are. This equation is always true. So this second guy has infinite solutions, right? So it turns out that if you were to graph this line and this line, they're actually the same line, right? They would be one right on top of the other. So that is what happens when you have infinite solutions. So this is just a little summary of what we just came up with, right? When you're solving a system of equations, if all the variables disappear, that's our clue that we're in one of two special cases. Okay? If you end up with a false statement, like we did in part A, where 1 equals 3, right? So if you end up with a false statement, there are no solutions to the system. If you end up with a true statement, like 4 equals 4 or negative 3 equals negative 3, that means there are infinitely many solutions to the system. All right, so that's the end of this demo. You can spend the last 5 minutes either going back to what you were working on or trying a problem or two from these activities. Next class is the quest. Survey/study, then the quest. The following class, I will remind you of this, and then we'll start on the activities.